Hey YouTube, what's up? Dr. T here, and welcome to the Altcoin Express and my hometown of St. Petersburg, Florida.
So, in this section, we will deal with all things pertaining to artificial intelligence, otherwise known as AI.
So DeepMind, a subsidiary of Google, is probably the foremost collection of artificial research PhDs in the world, with many hundreds across a range of disciplines, and they've just posted another wonderful series to their blog, Neural Scene Representation and Rendering. So we'll go through it and see what's in it, find out a little bit more. There is more than meets the eye when it comes to how we understand a visual scene. Our brains draw on prior knowledge to reason and to make inferences that go far beyond the patterns of light that hit our retinas. For example, when entering a room for the first time, you instantly recognize the items it contains and where they are positioned. If you see 3 legs of a table, you will infer that there is probably a 4th leg, and with some shape and color behind hidden from view. Even if you can't see everything in the room, you'll likely be able to sketch its layout or imagine what it looks like from another person's perspective. So here is a drawing with some easels and plaques on the board, and an elephant blocking out the little kind of brassy giraffe kind of thing there, and a birdie. These visual and cognitive tasks are seemingly effort to humans, but they represent a significant challenge to our artificial systems. Today, state-of-the-art visual recognition systems are trained using large data sets of annotated images produced by humans. Acquiring this data is a costly and time-consuming process, rendering individuals to label every aspect of every object in each scene in the dataset. As a result, often only a small subset of a scene's overall contents is captured, which limits the artificial vision system's training on that data. As we develop more complex machines that operate in the real world, we want them to fully understand their surroundings. Where is the nearest surface to sit on? What material is the sofa made of? Which light source is created all the shadows? Where is the light switch likely to be? And we have a little video, so we'll watch that next.
Giving computers the ability to see is a problem that we've been studying since at least the 1960s. What we want them to do is look at an image and understand it the way we do, to recognize how many objects are present, where they're located in 3D space, and what classes they each belong to. For instance, this is an elephant, this is a taxi, this is a plant, this is a human sitting on a chair, and so on. The way we do it currently is with a technique called Supervised Learning. We collect large data sets and manually annotate them to say what each image contains. And the computer learns from this data set how to interpret new images. The reason we need to do this is because the same underlying reality can look very different when observed from different viewpoints. For instance, if you're looking at me from the front, the light will be to my right, and if you're looking at me from behind, the light will be to my left, and so on. There are many problems with this method. One of the reasons is that it's a very time-consuming and costly process. And the second reason is that when humans label images in this way, they don't capture everything about the scene that might be of interest. For instance, relations between objects. The fact that I'm in a seated position probably implies that I'm sitting on a chair, there's a chair underneath me. But more importantly, it doesn't appear to be the way humans or animals learn. Human infants, for instance, learn so much about the world purely through observation and interaction. This suggests that there has to be a better way of doing this. So in this paper, we propose a simple method that learns to understand scenes purely from observation. We train neural networks that take one image of a scene and predict what it looks like from a different viewpoint. Imagine, for instance, a couple of cameras looking at a scene, and we say, given the image from camera 1, can you predict the image from camera 2? The computer will sometimes have to rely on something akin to imagination to fill in the gaps. for example due to occlusion where parts of the scene may be hidden from view. One of the most interesting characteristics of our model is that we can effectively fly through the computer's mind. We can ask it to smoothly move the camera in a new scene and visually inspect how well it can predict what that scene looks like from different viewpoints. This work takes us one step closer towards computers that learn to understand scenes the way we do. And crucially, it does this without any explicit human supervision.
That's interesting. We'll carry on. In this work, published in Science open access version, you can click on this, we introduce Generative Query Network, a framework within which machine learning to perceive their surroundings by training only on data obtained by themselves as they move around scenes. Much like infants and animals, the GQN learns by trying to make sense of its observations of the world around it. In doing so, the GQN learns about plausible scenes and geometric properties without any human labeling of the contents of space. The GQN model is composed of two parts, a representation network and a generative network. The representation network takes the agent's observations as its input and produces a representation, a vector, which describes the underlying scene. The generative network then predicts images, the scene from a previously unobserved viewpoint. Here we have a picture of a ball and a box in which the ball is, and the network is presumably going to do something. It's a little video, so we'll look quickly through that. And you can understand this is one of the important stepping stones in getting to artificial general intelligence. And we're really talking about an agent, a robot that can see and understand its environment. You can't go into a computer science course or any course without understanding what the environment is telling you, how to move about, taking the coursework. And this is their preparative build-up work to moving into more complex environments. And eventually they'll obviously have to get up to robots and learn to take a course in computer science, I guess. But this is their kind of way of building up the framework of algorithms that can understand the preemptives getting to artificial general intelligence, which is basically what they're trying to do. The presentation network does not know which viewpoint the generative network will be asked to predict, so it must find an efficient way to describe the true layout of the scene as accurately as possible. It does this by capturing the most important elements, such as object positions, colors, and room layout in a concise distributed representation. During training, the generator learns about typical objects, features, relationships, and generalities in the environment. Their shared set of concepts enables the representation network to describe the scene in a highly compressed, abstract manner, leaving it to the generation network to fill in the details where necessary. For instance, the representation network will succinctly represent blue cube as a small set of numbers, and the generation network will know how that manifests itself as pixels from a particular viewpoint. We perform controlled experiments on the GQN in a collection of procedurally generated environments in a simulated 3D world containing multiple objects in random position, colors, shapes, and textures with randomized light sources and heavy occlusion. After training on these environments, we use GQN representation network to form representations of new, previously unobserved scenes. We showed in our experiments that GQN exhibits several important properties. GQN generation network can imagine previously unobserved scenes from new viewpoints with remarkable precision when given a scene representation and new camera viewpoints. It generates sharp images without any prior specification of the laws of perspective, occlusion or light. The generative network is therefore an approximate renderer that is learned from data. So we have an observation and it's rendering and it does its thing, and I think they're cycling through that, so we'll move on. The GQN representation network can learn to count, localize and classify objects without any object level labels, even though its representation can be very small. The GQN predicts at query viewpoints are highly accurate and almost indistinguishable from ground truth. This implies that the representation network perceives accurately, for instance, identifying the precision configuration of blocks and make up the scenes below. So I've got some observations and it's doing its thing, rendering the three-dimensional aspects of the block just from one particular angle. It makes up a three-dimensional array of visual representations. The GQN can represent, measure and reduce uncertainty. It is capable of accounting for uncertainty in its beliefs from a scene even when its contents are not fully visible, and it can combine multiple partial views of a scene to form a coherent whole. This is shown by its first-person shooter and top-down predictions of the figure below. The model expresses its uncertainty through the variability of its predictions, which gradually reduces it as it moves around the maze. Grey cones indicate observation locations, yellow cones indicate query locations. Look at this. There's the thing moving, you're seeing its view, wandering down there, turns the corner, wanders around here, and so on and so forth. The GQN representation allows for robust, data-efficient reinforcement and learning. When given GQN compact representation, state-of-the-art deep reinforcement learning agents learn to complete tasks in a more data-efficient manner compared to model-free based learning agents, as shown in the figure below. To these agents, the information encoded in the generation network can be seen to be innate knowledge of the environment. So it presents some images, doing something, and runs through its training and spits out some data. GQN builds upon a large literature of recent related work in multi-view geometry, generative modeling, unsupervised learning, and predictive learning, which we discuss here in the science paper and the open access vision. It illustrates a novel way to learn compact, grounded representations of physical scenes. Critically, the proposed approach does not require domain-specific engineering or time-consuming labeling of the contents of scenes, allowing the same model to be applied to a range of different environments. It also learns a powerful neural rendering that is capable of producing accurate images of scenes from new viewpoints. Our method still has many limitations when compared to more traditional computer view techniques and has currently only been trained to work on synthetic scenes. However, as new sources of data become available and advances are made in our hardware capabilities, we expect to be able to investigate the application of GQN framework to high resolution images of real scenes. In future, it will also be important to explore the application of GQN to broader aspects of scene understanding, for example, by querying across space and time to learn a common sense notion of physics and movement, as well as applications in virtual and augmented reality. While there is still much more research to be done before our approach is ready to be deployed in practice, we believe this work is a sizable step towards our future autonomous scene understanding. And so they've got some readings and some downloads, PDFs and whatever for those who are especially interested in this area.